So, we are looking at Rayleigh flows. We have finished discussions on the concepts of Rayleigh flows, theoretical part and also the equations. So, let us apply them. Always remember the Rayleigh curve, it is very important. So, if you can keep this in mind that this is the qualitative description of how a Rayleigh curve looks like. These in here stagnation temperatures keep changing. So, one should look at stagnation points also, and there is a maximum entropy point which is for Mach number equal to 1, and there is a point where there is maximum enthalpy, or T is temperature is maximum. Subsonic branch is at the top and supersonic branch is at the bottom, and heat addition always drives the flow towards sonic conditions. Maximum amount of heat that can be added is at the sonic point, which at the critical point. So, if you take any point and take the critical point, the difference of stagnation temperatures will tell you the maximum heat that can be added. So, this is the highlight. Now, let us look at some of the problems. This is problem number 1. The Mach number at the exit of a combustion chamber is 0.9. So, always useful to draw a schematic, a constant area duct, and Mach number at exit M2 is 0.9, and ratio of stagnation temperatures at exit and entry. So, T02 by T01 is given 3.74. If pressure and temperature of the gas at the exit are 2.5 bar, P2 is 2.5 bar and T2 is 1000 degree centigrade respectively. Determine Mach number, pressure, temperature. So, we need to know M1, P1, T1, heat supplied, what is Q, and the maximum heat that can be supplied, and then Q star corresponding to the entry conditions. Okay. So, gamma is given, gamma is 1.3, please make a note of that, and Cp is given 1.218. So, for this what do we look at? So, we know T02 by T01 and we know what is M2. So, from there we should be able to get what is T01 by T01 star, and then therefore get M1. Is T02 known? It is this temperature, that is static temperature is known. So, T2 is 1273 Kelvin, and T02 is not known, but Mach number is known. So, we directly go and look at the isentropic relations and find out what is T02 by, or T2 by T02, and T2 by T02 is 0.8916 for M2 equal to 0.9. That means T02 from here you can find it is 1427.77 Kelvin. Okay. So, T02 is you can be easily found from here. Now, we know T02 and we know T02 by T01. So, T01 can be found is T02 by T02 by T01, which is 1427.77 divided by 3.74, which is 381.756 Kelvin. Okay. So, we have found what is the inlet stagnation temperature. Now, how do we get what is the inlet Mach number? So, T02 by T01 is T02 by T0 star divided by T01 by T0 star. So, they now lie on the Rayleigh curve, this T0 star is the same. So, T02 by T0 star can be found for Mach number is 0.9 and that is 0.9914. So, we get T01 by T0 star is T02 by T01 divided by T02 or T02 by T0 star divided by T02 by T01. Okay, yeah. So, this is correct. So, we will get this value now T01 by T0 star. This is it turns out to be 0.265. Now, we can go back to the calculators or the charts and find out what is the corresponding Mach number, and Mach number M1 is 0.2597. So, we now have the value for the Mach number 0.2597. So, now how do we get the pressures and the temperatures at the entry? For that we need P2 by P1. This is P2 by P star divided by P1 by P star for the Rayleigh flow, and P2 by P star is known for this particular case 0.9. So, P2 by P star is 1.12 divided by P1 by P star for the Mach number 0.2597. Okay, so, for that you need to find what is the P by P star, and therefore, that P by P star is 2.1144, and therefore, from here you can get P1. So, P1 can be got from here which is 4.7187 bar. So, you see that P1 is higher than P2, which is to be expected in a subsonic flow. So, it is 0.9, it is a subsonic flow, and therefore, P1 is greater than P2. What about T2 by T1? Similar lines, T2 by T1 is T2 by T star by T1 by T star, and T2 by T star we have the value it is 1.0166, while for for this case, which is T1 by T star, it is 0.395, and therefore, you can get T1 is 377.54 Kelvin. So, that is now a smaller temperature, that is in keeping with the heat addition. What is the amount of heat added? Q is Cp multiplied by T02 minus T01. In this case, it is 1.218 multiplied by T02 minus T01. So, 1427.77 minus 381.7566 turns out to be 1274.04 kilojoules per kg. Okay. So, this is the amount of heat added. We know Mach number is 0.9, so it must be very close to the Mach number 1, which is the maximum heat being added, but slightly less than that. So, what is the maximum heat that can be added? We know the Mach number M1 is known, it is 0.2597. So, corresponding to this, we can get T0 by T0 star, it can be found, and that is 0.265. and from here from this point we can calculate what is T 0 star, which is because T 0 is known. So, T 0 star is 1440.59 Kelvin. Therefore, maximum heat Q star, that is maximum heat, is Cp T 0 1 T 0 star minus subtracted by T 0 1. Okay. So, this is what it is, and this is you can substitute the values. 1.218 is the value for Cp, 218 multiplied by 1440.59 subtracted by 381.756. So, this is 128989 kilojoules per kg. So, it is very close to since we have a Mach number at M2 is 0.9, we should expect that this value will be very close to the Q that was added in the previous case, and they are quite close 1274 and 1289. So, this is a direct problem in Rayleigh flow. So, it is always useful to keep this Rayleigh curve in mind when you are solving such problems, and look at the charts, look at corresponding values of T 0 by T 0 star, P 0 by P 0 star. Idea is the sonic condition remains a reference point. Okay. So, now we go to the second numerical. In this air, the properties are given: gamma equal to 1.4, R is 0.287 kilojoule per kg, Cp is given kg Kelvin, and Cp is also given, flows through a constant area duct of diameter 0.02, and that is connected to a reservoir at a temperature of 500 degree centigrade and a pressure of 500 kilopascal by a converging nozzle. Now, heat is lost at the rate of 250 kilojoule per kg. Determine the exit pressure and Mach number and the mass flow rate for a back pressure of 0 kilopascal. What is meant by 0 kilopascal here is very low pressures at the exit of this. Determine the exit pressure and Mach number when a normal shock stands in the exit plane of the duct. So, what is given here is that there is an air reservoir, a much larger reservoir, and that is getting connected to a duct by means of a convergent nozzle, and then you have a duct where there is heat is getting removed. So, heat is removed. So, you can see that in Rayleigh flows both heat can be added or heat can be removed. It is not, there is nothing constraining heat removal process. So, we are having two processes here. There is a convergent nozzle. This is an isentropic flow. So, it is isentropic here in the nozzle, and thereafter you have a Rayleigh flow here. So, a Rayleigh flow here, and what is given is reservoir pressures and temperatures 500 degree centigrade. So, this is T naught and P naught is 500 kilopascal. So, always useful to draw the Rayleigh curve, and if in this case you are representing this Rayleigh curve. So, what is given is that at the exit the pressure is very low and considered as 0 kilopascal. What does this imply? The flow should expand rapidly. If you have a convergent nozzle and you have a large pressure differential across it, then the obvious case is that you will get Mach number 1 at the minimum area point. So, at this point Mach number should be equal to 1. Okay. And after that you have a Rayleigh flow and there heat is removed. So, let us just see this point on a Rayleigh curve TS diagram. Okay. So, this is the case that is being discussed. Okay. Draw the Rayleigh curve. This is the maximum stagnation temperature point, and what you find is that at the entry to the Rayleigh curve Mach number is 1, m is equal to 1. So, the first case it should have gone from a stagnation temperature say T naught over here. From that point it has gone there has been an isentropic process to the point where Mach number equal to 1. Thereafter heat is removed. So, it follows this. Okay, this is a subsonic branch, but now if you remove heat from this point it will follow the supersonic branch, because Mach number will increase now. So, it will go to further supersonic values. If you remove heat here it will go to supersonic values. So, it follows the supersonic branch over here, okay, to another. So, T0 will be lesser, it will be a lower T naught because heat is being removed. So, what else is given here? So, P0 T0 is given, P01 is 500 kilopascal, T01 is 500 degree centigrade, and heat removed is given, Q dot is 250 kilojoules per kg. Okay, Cp is given, Cp is 1.0045 kilojoules per kg and kg Kelvin, okay, and gamma is 1.4, R is 287 per kg Kelvin. So, what should be the Mach number at point 2 M2? How do you find this out? We know that heat is being removed. So, Cp T02 minus T01 is equal to minus Q dot or minus Q. So, this is 1.0045 multiplied by T02 is not known minus T01 is known, 773 Kelvin, 773 Kelvin is 250 kilojoules. From here we get T02 which is 524.12 Kelvin. From here we can get what is so this corresponds to directly, if you do T02 by T01, this is equal to T02 by T0 star. Okay. So, so this is directly the case where you have. So, always we look at heat addition problem. So, this we should see that star is here. So, this we are looking at is T01 by T02. Okay, T0 that will be T0 star by T0. So, that gives you the value for T0 by T0 star directly, which is 773 divided by 524.12. It is so from T02 by T01, from this particular point we can always get okay. So, it should be T02 by T0 star, which is 524. So, we should be careful here, 12 by 773. This is the reference point and M2 is lower. So, this should be correct. So, this is not correct, and this is equal to 0.678 and the Mach number corresponding to this is 2.7613. We also have to look at the supersonic branch. So, if you look at the supersonic branch, you will get the solution 2.7613. So, M2 is known. So, now if M2 is known, then it is easy to find the rest of the values. directly this is the star value that we are looking at. So, if we know P2 by P star, then we will know the pressure. For this, the P2 by P star is 0.T0557. So, and we need to find the static pressure at this particular point at point 1, and this is at point 2. We know it is Mach number 1, and the stagnation pressure is given. From there we can find using isentropic relations P1 is nothing but P01 by P star. From there we can find out using isentropic relations what is P star, or what is this pressure. P star is 264.15 kilopascal. So, once P star is known, then P2 can be found, and P2 is 54.3013 kilopascal. Okay. So, it is consistent with the Rayleigh flow curve. Pressure will reduce. So, it has reduced. Now, what about mass flow rate? Mass flow rate can be found m dot is rho 1 A1 B1, and the area of the duct is given 0.02 meter diameter is given. So, area is A1 is pi by 4 multiplied by 0.02 square. Okay, so, area is known, which is something like 3.14159 into 10 power minus 4 meter square. Then P1 is known, T1 is also known, T1 can be found out. Therefore, T1 is from T01 by T star, an isentropic process. T1 is 644 Kelvin. So, 644.167, and therefore, you can find the density rho 1. Rho 1 is 1.4287 kilogram per meter cube, and velocity corresponds to Mach number equal to 1, which is acoustic velocity at 644 meter square, 644 Kelvin, which is acoustic speed is 508.74 meter per second. Therefore, mass flow rate is 0.228345 kilogram per second. Okay, so this was a different kind of a problem where there was heat removal. So, it is negative heat that is taken out, minus q dot, that is 250 joules is taken out. So, therefore, T02 reduces, that has to be understood here, and we should be careful when we look at this problem, because the direction of heat transfer is in the opposite direction, but it is starting from the reference value. So, T01 is T0 star. So, T02 by T01, if you take, it becomes T02 by T0 star, and therefore 0.678, and therefore you get M2, and from M2 and M1 we can get all other values. So, with these two problems we come to the end of discussions on Rayleigh flow. So, we have now looked at all kinds of different cases of flows in ducts. It can have variations in area, it can have friction, or it can have heat addition with constant area. Now, in real applications, there is no real distinction between all these three. They may occur together. So, is it possible to analyze such flows? Here when we looked at only single drivers, like if you consider only constant area, there is no friction, no heat addition, then you are able to do isentropic flows and get closed form solutions. Then you considered the frictional flow, where you considered a constant area duct and there is only friction, and there you are able to again get closed form solutions in Fano flow. Similarly in Rayleigh flow, but what if there is a combination? So, we will introduce the topic which is a generalized quasi 1D analysis, where you can have combinations of driving potentials. How do we analyze this problem? What are some interesting kind of results that might come about in the next class? So, thank you.